Hi, everybody. I think we can start. So this is the first seminar of the new season of the Newton 1665 seminars. Given the situation, we decided to keep the name Newton 1665. I hope that you guys are doing well with your families and friends. And back to physics, it's a pleasure to start with Professor Maldacena from the Institute, who will tell us a story about magnetic black holes, wormholes, and how to make them traversable. So Juan, please, the stage is yours. Enjoy.
Okay, thank you. Can you hear me? Yeah, well, thank you for the invitation.
Yes.
And I hope everyone is well. And so let me see, let me share my screen. Okay, so this talk will be based on some papers recently that were written recently in the last few years. I'll try to review a few papers. The idea about traversable wormholes started with the paper of Gao, Jefferies, and Wall. And then we extended it to write four-dimensional traversable wormholes. Then I'll discuss, I actually will start with some discussion of magnetic black holes. And then finally we'll discuss some traversable wormholes that are very big. Okay, so the motivation is, the first motivation is about the magnetic black holes, is to point out some interesting properties of magnetically charged black holes in the standard model. And then we'll use some of these effects to construct traversable wormholes. And finally, we'll postulate a special type of dark sector which leads to traversable wormholes. Now, these solutions were obtained as a kind of side effect of research on the relationship between quantum mechanics and gravity, and in particular, the relationship between entanglement and space-time connections. I'll discuss that bit at the end, but these constructions themselves can be phrased completely within the language of effective field theory, the effective field theory of general relativity plus quantum fields. And I will take this perspective in this talk. These wormholes are curious configurations which are not possible classically, but are possible due to quantum mechanics. And they involve an interesting interplay between different kinds of physics and are fun solutions. So first I started with the discussion of magnetic black holes. These are magnetically charged black holes in the standard model. The main motivation is that these are very long-lived configurations compatible with the laws of physics as we know them, provided, I guess they can exist provided the U1 of a standard model is compact. Maybe they were produced in the early universe, and so they are interesting primordial black hole candidates. And we should understand their properties if we want to discover them or rule them out. And they have some interesting properties because they can have very large magnetic fields. So the interesting properties that I want to highlight is that they are in some sense a natural way of generating very large magnetic fields that stay for a long time. Also, the fact that the Electroweak symmetry can be restored around the black hole, and that fermions lead to a large number of effective fields that go in and out of the black holes, and these effects will enhance the effects of Hawking radiation. And finally, that they can catalyze baryon decay through an effect somewhat similar conceptually to the Kalan-Ruakov effect. Now, usual Schwarzschild black holes would evaporate before the age of the universe if the mass is less than 10 to the 12 kilograms, the mass of a mountain. And on the other hand, charged black holes can have a range of masses, but these masses should be always bigger than some minimal mass that is proportional to the charge. Such black holes would evaporate to extremality if all charged particles are very heavy. And for this reason, they can be very long-lived. In principle, they are not completely stable because you can create some massive charged particles and they can decay. But if the masses are high, if the masses of the charged particles are high, they can be very long-lived. So in particular, magnetically charged black holes can be very long-lived if magnetic monopoles are very heavy. Let's say they are at the gut scale, for example. So in this situation, you can have black holes, magnetically charged black holes that weigh, let's say, a few kilograms, and you could carry them. I mean, they're light enough, you could carry such black holes around. Now, there is a question of whether they could actually exist, or maybe they are already ruled out, where there are bounds on their number. And the step 0 is to understand a bit their properties. And recently there have been some papers, for example, this one trying to put some bounds on their number and their proportion relative to dark matter and so on. So the starting point is the charged black hole solution. And here we see the extremal charged black hole solution. It has essentially the geometry has only one parameter, which is RE, which typically gives us a basic size of the radius of this geometry, the scale for the geometry. And the black hole geometry develops in this extremal limit a long neck whose geometry is basically AdS2 times S2. So a simple two-dimensional space with constant negative curvature times two sphere. So the radius of the sphere becomes constant as we go deep down this big gravitational potential well. This black hole this configuration is supported by a magnetic field, which we can write this way, and where Q is an integer. This is related to the ordinary magnetic field by a factor of E, and the magnetic field has this expression. And RE, through the Einstein equations, there's a connection between the charge parameter appearing here and RE, which is this one here, which says that RE in Planck units is proportional to the charge in, let's say, integer units. So we make the charge bigger, we make, of course, the black hole bigger. Now, there are two scales that are relevant for the analysis of this problem. So one scale is the size RE that we've already discussed. And the second is the square root of the proper size of the magnetic field. And this is important because it sets the energy scale of the Landau levels when we have charged particles. And something important to note is that the larger Q is, the smaller this magnetic, the smaller this quantity is. So the charge becomes bigger, but the flux becomes more dilute. And well, also vice versa, if you have a smaller black hole, you would have a higher and higher magnetic field. Now, let me remind you about Landau levels for charged particles in the presence of a magnetic field. So we have a dispersion relation, which is boost invariant along the direction of the magnetic field. And the four-dimensional field becomes a sequence of two-dimensional fields whose effective 2D masses are given by the energies of these Landau levels. And the precise, the Landau levels have a contribution from the orbital part and a contribution from the spin. So for particles without spin, like scalars, we simply have a contribution proportional to the size of the magnetic field. For spin and halves, the lowest energy is, there is a precise cancellation between the orbital and spin energy. And for spin 1, there is actually the magnetic moment contribution is bigger than the orbital one. And so we have an actual negative contribution due to the magnetic field. So the cancellation for spin and half can be understood as a consequence of the Carrel anomaly, an anomaly matching between 4D and 2D. For a vector, the fact that this is negative implies that for very large magnetic fields, when that is larger than the mass of the vector field, we'll have an instability. And this will be an issue for the W boson. So magnetic fields can be screened in non-abelian theories. And of course, there are other, here we've talked only about the lowest Landau level, but there are other levels whose spacing goes in units of 2 times this size of the magnetic field. Okay, so main message is that the magnetic fields can be very high, and the largest value of the magnetic field occurs in the near horizon region, of course, where R is of order Re, so that's the value. And using the expression for Re that we had before, we see that the magnetic field, as promised, decreases when we make Q large, but it starts from a very high value of order 1 over L blank for Q very small. So there is a large range of Q where we can have very high magnetic fields. For example, this electroweak instability that we discussed, so that occurs when F is equal to mw squared. That happens for a black hole whose magnetically charged black hole whose size or mass is written here. So this is the charge in integer units, but perhaps a little more clearly physical is that the mass would be roughly the mass of the order of the mass of the Earth, and the radius would be a few centimeters, roughly the size of a pool ball. And so if we have a black hole of this size, already the magnetic field will be high enough that we can create a region where the electroweak symmetry, where we have some kind of condensate of W bosons. So we expect that this condensation of the W bosons will screen the SU2 part of the magnetic field. So the ordinary magnetic field, of course, is a combination of the magnetic field in the U1 of the standard model and the SU2 of the standard model. And after the SU2 part is screened, we expect that only the hypercharged magnetic field is left over. Now the Higgs is charged under the hypercharge. And as we saw before, when we have a scalar field that is charged under magnetic field, there will be a non-zero energy from the Landau level. And so for very large magnetic fields, this will make it convenient for the Higgs field to have zero BEV. So what we conclude is that for very large magnetic fields, the electroweak symmetry is restored. And this is indeed something that has been known for a while, and it was analyzed in a very nice series of papers by Ambjørn and Olasen in flat space. So what this implies is that the black holes have some, when they are sufficiently small, they have some structure around them, which we can call the electroweak corona, sort of somewhat similar to the solar corona in the sense that it's dominated by magnetic fields and so on. So far away, we have the usual electroweak vacuum, and we have ordinary magnetic fields. As we go in, there will be a surface where the magnetic field becomes of order the mass of the W boson, and then there will be a region where the W boson field is non-zero, and also the Higgs is displaced from the minimum of the usual minimum of the potential. And then finally, there is a surface where the magnetic field is equal to the mass square of the Higgs. And within this region here, the electroweak symmetry is restored. We have that the Higgs field has zero BEV, and we have purely hypercharged magnetic field. We didn't find a precise solution in this transition region. This type of, we expected that it is locally the same as the solutions that people have discussed for constant magnetic fields in flat space, where there is some kind of structure which is not spatially uniform that develops, somewhat reminiscent of the Abrikosov vortex lattice, but a little bit more complicated because it's more non-abelian. And so that will be the structure here. It's not spherically symmetric, and so on. Anyway, so the important point is that for small black holes, so black holes that are smaller than the size of a pool ball, this electroweak corona can be much bigger than the actual size of the black hole. So as we saw before, the black hole size goes like Q times L Planck, and the radius of this electroweak corona comes from this formula, goes like square root of Q times 1 over mw. of course, 1 over mw is much bigger than Planck, and for that reason, there is a range of Qs where this is much bigger than this quantity. Eventually, for a large enough Q, there is no such effect, and the black hole is I mean, we have ordinary magnetic field, and we don't have any of these effects. Also notice that the size of this corona is much bigger than 1 over mw. So we have a big sort of macroscopic, we can have a macroscopic region where the electroweak symmetry is restored. So we have one of these black holes whose size is of order a pool ball or a little smaller, will have a macroscopic region where the electroweak symmetry is restored. So this is saying the same thing. So plotting just here the radius for various charges and well, also as a function of the mass. And so this is the black hole of the size of a pool ball. And so in general, this is the radius of the corona, which is much bigger than the radius of the black hole. In the same way that there is a QCD, that there is an electroweak corona, there is a kind of QCD corona where the usual QCD vacuum is distorted, and one could study that in more detail. I have not done it, but so there is some region also in between here. Now, as we discussed, the fermions in the region where the electroweak symmetry is restored are all massless because the Higgs is 0. And they're all charged at the magnetic hypercharged field. And therefore, they have a 0 energy Landau level with a degeneracy which is equal to the charge of the black hole times the hypercharge of the particular field that we're talking about. And this leads to a bunch of massless modes that move along the radial direction, and they can be viewed as modes that are moving along the magnetic field lines. We have roughly 1 mode per flux quantum. So we have a bunch of magnetic field lines. We have modes which have roughly the size of the lowest Landau level orbital, or just 1 flux quantum. And so you can go through the matter content of the standard model and find how many effective 2D modes we have. Some, I mean, of course, we have chiral fields in the standard model, so some, this will also lead to chiral modes in 2 dimensions. So some of the modes will be purely left moving, and some of the modes will be purely right moving. And of course, 2D anomalies are canceled because 4D anomalies are also canceled. Okay. Now, when this is the set of fields within the inside this electroweak corona, and after they cross this corona, some well, they will typically all get some mass, but some will get more mass than others. The neutrino, on the other hand, becomes neutral, and we lose this large degeneracy of all these Landau levels. Yeah, something I didn't emphasize is that Q is very large, so there is a large number of these 2D fields that we were discussing. Now, in principle, to find the proper infrared dynamics, we also need to consider dynamics of the gauge fields, U1, SU2, and SU3, and for now, we will ignore them. And, in fact, we will ignore them throughout this talk. Now, the fact that we have all these effective 2D massless modes implies that Hawking evaporation is greatly enhanced relative to the case where relative to the uncharged case, because we have this extra factor of Q in the Hawking radiation rate. So this is the radiation rate. This is sort of the black body formula for a 2D system. And since we have Q species of 2D fields, we have this formula. If we compare to a Schwarzschild black hole at the same temperature, then we have the 4D black body formula times an area factor. It's due to the dependence of the temperature on the size, we find that this also goes like T squared, but without the factor of Q. So for example, if we have a black hole, an uncharged black hole of the mass of a big mountain, the 10 to the 12 kilograms we already discussed before, the evaporation time of such a black hole is the age of the universe. On the other hand, if we had a black hole with the same mass, with an order 1 deviation from extremality, the lifetime would be just a millisecond. Okay, so that's the time scale to decay to extremality, and well, extremality is approached exponentially. So that's the time scale in the exponential. Now, as the temperature becomes smaller than, and for that, such a black hole, the temperature will be of order GeV. It would be emitting a huge amount of energy. And as the temperature becomes smaller than the electron mass, there will be exponential suppression in this emission rate, and so on. Now, black holes are expected to violate global symmetries. So in principle, baryons could go in and leptons could come back out, or some equal mixture of baryons and leptons. And in this way, we can they could catalyze proton decay. So you could imagine having a relatively light black hole, say 100 kilograms, that we could use to get a significant amount of power. So this would have a QCD radius of the order of the size of an atom. So if we get sufficient number of baryons in its vicinity, we could get them to fall into the black hole and be emitted as Hawking radiation or energy. Now, in addition, there are Fowler effects that are unsuppressed inside the corona, and this could also lead to baryon number violation. Now, one question is whether these black holes could be produced at all by some in the early universe. And here, first, we'll remind you of the production of uncharged black holes. So we have large primordial fluctuations at some scales. So here we depict the primordial fluctuations. Let's say at very long distance scales have small amplitude, but if for some reason the inflaton potential has some features that enhance the fluctuations at particular wavelengths, then after reheating, we might produce black holes whose size is determined by the length scale at which we had enhanced fluctuations. And this is a simple mechanism and fairly reasonable mechanism for producing black holes. Of course, it requires some features in the potential that maybe slow down the evolution so as to enhance the size of fluctuations at some regions. And so that's one way to do it. And there are other ways that people have discussed, including phase transitions or some other type of violent process after the end of inflation. Now, if you want to produce magnetic black holes, you can have a kind of variation of this mechanism. That's one possibility. Maybe there are others. And here we combine an idea which is in these two papers. So first, the idea is to have to produce a large number of monopoles and anti-monopoles after the end of inflation. So here we have in red the monopoles and in blue the anti-monopoles. Now, when and in addition, we have the large fluctuations in the large primordial fluctuations that we had in the previous transparency. So now we will produce some black holes as we were producing before, and some of these monopoles and anti-monopoles will end up in these black holes. But when these monopoles and anti-monopoles are produced, there are some fluctuations in the number that each black hole will swallow, and we expect that the net charge will be some factor which will go like square root of n. So square root of n will be like the typical fluctuation in the charge of these black holes. And as we had discussed, they can evaporate quickly, well, less than the age of the universe. And so we would find them now as extremal charged black holes, magnetically charged black holes. Now, this is, of course, not what we expect in the simplest models of inflation, but it doesn't seem to be completely outrageous. And furthermore, maybe there are other mechanisms for producing them. I don't know, maybe some of you will come up with some other mechanisms for producing them. So I think the main conclusions of this part of the talk is that magnetic black holes are interesting objects and we could look for them. I would bet they probably don't exist, but we should make sure not to miss them. It would be very cool if they existed, but they certainly are not produced by the simplest models of inflation and reheating. Okay, so now I'll change track slightly a little bit and we'll go on to the discussion of wormholes.
Can I ask something?
Yeah, please.
My name is Sergei Petkov.
Yeah.
So are neutrinos playing any role in the evaporation of black holes?
In the evaporation?
Of
Yes,
magnetic black
yes. They play a role when they are when you have this this corona in the corona region. So in the region where the electroweak symmetry is restored, the neutrinos have large degeneracy and are part of the radiation that is coming out of the black hole.
Is it a significant part?
Yeah, it's a significant part. Yeah. So coming out of the black hole, yeah, maybe I'll give a. Yeah, so in this region here, what is coming out of this black hole in the center is roughly equal in all the different fields of the standard model, from the top quark to the neutrinos. Then when we get to this region, of course, something like the top quark would get a very high mass and would probably be reflected back. Something like the electron will just go through. The neutrinos lose the large degeneracy, and I expect that the flux of neutrinos would probably be smaller. It's a complicated process, which I don't completely understand. And of course, would be dependent on the temperature. If the temperature is high enough, you'll have the neutrinos also escaping very easily. So yeah, indeed, most of the radiation, so for some range of temperatures, would come, let's say, in electrons and neutrinos, or maybe even mostly neutrinos. Exactly what will come out depends on what happens through this transition region.
Okay, thanks a lot.
Sure, yeah. I mean, one could get the picture that the whole, all these fields become, well, will reach some kind of thermal equilibrium in this region, and then they will leak out towards the outside. So the radiation in neutrino, if I had to guess what it is for temperatures higher than the neutrino mass, I would use just the black body formula with the area of the corona here. But I haven't studied it in detail. Okay, so is there any other question about this part? Okay, so now we'll discuss wormholes. So the simplest wormhole arises when we look at the full Schwarzschild solution. So that's the old solution that Schwarzschild wrote, but analytically extended, maximally analytically extended, as was understood by these people. And this solution describes not one black hole. So this region here is the exterior of one black hole. This is a flat space far away, and these lines here are the horizon. But it really describes two black holes in two separate universes that are connected through the interior. Now, the interior is a bit like a collapsing universe, and if you send a signal from the right exterior into the interior, that signal cannot make it out to the left exterior. So these wormholes, we call them non-traversable. They kind of are spatial geometries that connect the two sides, but are not cannot be used to send a signal. They are time dependent, and they essentially collapse before you can send the signal from one side to the other. So if you start trying to go to the left side, you find that the size of the sphere shrinks and eventually shrinks to 0 here before you can exit on the other side. And you could also say that the distance between the two horizons is growing, and even though they touch at this point, they start moving apart from each other, and that prevents you from crossing. We could have another configuration which is somewhat similar to the previous one. So we could have those two black holes not be part of two separate universes, but they could be in the same universe, but very far away, and in such a way that the geometry near each of the two black holes is similar to the one we saw before. And in this situation, we have, again, a spatially, well, some wormhole that, again, is not traversable. But if you are, let's say, these two black holes could be, let's say, 10,000 light years away. But if you are 1 meter outside from this one, and there's a friend of yours which is 1 meter outside this one, the distance in the ambient space is still 10,000 light years, but the distance through the wormhole would be 2 meters. So that's a distance, but since the wormhole stretches as time progresses, you cannot be able to go in and then out on the other side. Now, there is a general reason why such wormholes are not traversable in general relativity, and it's due to the positive, to the integrated null energy condition, which says that the integrated null energy condition should be positive. This is kind of a welcome result, because otherwise, if they were traversable, we would be able to violate the principles of relativity. We would be able to send signals faster than light. Now, quantum mechanics can violate the null energy condition. So null energy condition is locally this one, classically. But there can be regions where t++ is less than 0. But what's relevant for these constructions is really the integrated null energy condition. And this integral is 0 in flat space. And it was proven recently that it's always 0, even for interacting theories. But it can be violated. So an example where it's violated is, let's say, a 2-dimensional theory in a cylinder. So in such theories, there is a Casimir energy contribution or a ground state energy contribution, which is negative. And if you have a light ray that goes around the cylinder, you'll get a negative contribution to this quantity. So the true quantum condition that is supposed to be valid in all cases is believed to be the so-called achronal average null energy condition, or sometimes AA-neg. So this is the same as this condition, except that gamma is supposed to be the fastest null ray that you have in your geometry. By fastest, what we mean is that there are no 2 points on the light ray that are time-lag separated. So in the case of the cylinder that we discussed, if you go once around the cylinder, those 2 points, the starting point and the end point, are separated by a time-lag distance. And so such a light ray does not obey the achronal condition. But if the achronal condition is supposed to be obeyed, then we believe that relativistic quantum field theory obeys this condition here. And that condition is enough to forbid the so-called science fiction wormholes. So science fiction wormhole is a wormhole which you can use to travel faster than the speed of light. And the answer from these results, this condition is partially, well, it was, of course, it was proven in flat space, but in this curved space situations, it's a conjecture. Of course, it's a conjecture with no counterexample, and it's believed to probably be true. And it's interesting that this condition, which is a condition of matter that depends on quantum mechanics and so on, it's enough to ensure the consistency of general relativity with matter. By consistency, what I mean is that general relativity was built on the idea that there is a maximum speed for the propagation of signals. And if these geometries were possible, then that initial postulate would not be correct. So the theory itself says that the original postulate is not correct. So that I would view it as an inconsistency. But fortunately, this doesn't happen, and it depends on interesting properties of matter. Now, so that's nice, but this does not forbid, these quantum conditions do not forbid the situation where we could have a sort of long wormhole. So by a long wormhole, what I mean is the following. So imagine that it takes some time d to travel between the 2 mouths of the wormhole. So a light ray that goes between the 2 takes some time d to go. D is the distance between the 2. But it could be that traveling through the wormhole takes some longer time. So that's what I mean by a long wormhole. And that would be a time, as long as it is a time bigger than d, then it would not violate causality. And furthermore, this yellow light ray would not be an achronal light ray. So for this light ray, we don't have the positive integrated null energy condition. And so the integral of the stress tensor through this geometry can be negative. At least the quantum field theory would allow it to be negative. And if that's negative, then this geometry is allowed. So somehow the this geometry itself, in order to exist, it requires this this integrated negative condition. I didn't explain it before, but let me just explain now why. So there is an equation called the Ray-Chaduri equation, which tells us how gravity focuses light rays. Initially parallel light rays or initially divergent light rays, they tend to be focused by matter. So the matter focuses it more than otherwise. Now, in order to have this geometry, what we need, we would have, imagine light rays that are coming in through the wormhole. So they initially are convergent, but as they go through the wormhole, they become divergent again. And that's a situation which would not be possible if the t++ was positive everywhere, or even if the integral of t++ was positive. So in order for light rays to sort of converge onto the mouth and then diverge on the other side, we need that the integral is negative. And as we said, it is possible that it's negative in quantum field theory in this situation. So we'll now discuss this type of wormholes and what ingredients are necessary for getting these solutions. They are traversable, so that's kind of interesting. They will be close to black holes, but they are actually not black holes. They don't have a horizon. And they do not allow for faster than light travel. So if you're a science fiction enthusiast, this is bad, but if you think if you think about the principles of relativity and so on, that's a welcome sign. Now, it's also important to note that the observer proper time through the wormhole could be much shorter than the travel time outside, and we'll see how that works. And the constructions that we will discuss in a second require some special matter, but it's still matter obeying the rules of quantum field theory. We do not require any exotic matter. So in this previous discussions of wormholes have involved exotic matter. By exotic means matter violating the null energy conditions. So first we'll start discussing the simplest example. And the matter we require in this simplest example consists of a U1 gauge field and massless charge fermions. So just Einstein theory plus U1 gauge field plus massless charge fermions. And this could be the standard model at very short distances where we can neglect the mass of the fermions, and the U1 would be the hypercharge. So this you could view it as a toy model for the physics at very short distances. But for now, we'll consider this theory on its own. First solution we'll discuss are near extremal black holes. So that's the same geometries we were discussing before. Again, charged black holes with magnetic charge. There is this near horizon region. And we'll start with a pair of black holes with opposite magnetic charge. So one positive charge, the other one negative charge. And if they're extremal, they contain a very long neck, very deep. It's like a big, very deep gravitational potential well. There is a redshift factor that is becoming very, very small as you go down here. And now we connect the two throats. We connect the throat of one with the throat of the other. So both are some ADS2 times S2 geometries, and it is possible to connect these two throats. And this only requires a sort of small deformation of the geometry. And at this stage, there is one free parameter, which is somehow the length of the wormhole. We'll define exactly what the length is, but roughly intuitively for now, we can say that how long this manifold is when we connect them. So we can connect them either in a deeper place or in not so deep place. And that is the free parameter that we have. And as we'll discuss, this requires by a small deformation. It's just that it's a small deviation from the solutions of the equation. So this configuration is not a solution of the vacuum Einstein equations. We'll make it into a solution in a second. Before making it into a solution, we'll consider the dynamics of the fermions, and a single 4D massless fermions will give rise to Q two-dimensional massless fermions that move along the magnetic field lines. This is the same effect we discussed before, and somewhat similar to the particles moving in the magnetic field of the Earth. And the lowest Landau level has zero energy, as we discussed before, And so we get these Q fields, that Q is the charge of the magnetic black holes, that will now move on a circle. So the circle is the following. So we have the magnetic field lines that come out of one mouth and then go into the other mouth and then go through this whole configuration, and those form closed circles. And so we have effectively massless two-dimensional fields moving on a circle. And for this reason, we will get some negative energy. So when you have a two-dimensional field on a cylinder, on a circle, there is negative energy, which is proportional to 1 over the size of the circle times Q. So this is the result that we would have for a flat cylinder. And here we'll define the length L for now to be such that the Casimir energy that we get is actually this expression. So the length here could be defined as the time it takes for a light ray to go into one mouth and then come out of the other mouth, as seen from the outside observer. So this is one more precise definition of what we are meaning by the length L. It's not equal to the proper length of a spatial circle here. So what I just defined is what we mean by the length L. Now, the idea is that, so we made an ansatz for the geometry, and then we'll solve the Einstein equations. So I'll discuss in the next transparency is the solution of the Einstein equations in this region of the geometry. Okay, and the structure that this equation, well, you can just write the equation exactly, write the equations and then solve them. As I said, it was a small deviation from something that is a solution, so you can do it perturbatively. Here in this whole solution, the expansion parameter is 1 over Q. So it's the mechanism that, I mean, before discussing this, I should say that one typically suspicious of a solution that is obtained by balancing classical effects against quantum effects, because you might worry about the next correction, so in the G-Newton expansion. But what happens here is that the classical, the original classical effects are strongly suppressed, so the solution is very close to, the configuration is very close to a solution if we had no matter. And so the whole configuration has a nearly zero mode, which is this length parameter L. And then you balance that against the classical contribution to, for example, the energy. So one way to think about this balance is to calculate the energy of the solution. There is some energy that comes from the deformation of the geometry that we did. And for large L, this is a small deformation. It's proportional to 1 over G-Newton, so it's classical. And then there is the quantum energy. It's enhanced by Q. And then if you minimize this, that's a quick way to get to fix this length parameter. You find this length parameter is large and proportional to Q times the size of the two black holes. And this solves the Einstein equations in the wormhole region. So once you fix the length to this value, you can solve Einstein's equation. So this is a quick argument. You can do the more precise argument. You get exactly the same answer, even with the factors of 2 and so on that I haven't put in here, but you can put them if you want it. Okay. So if you didn't follow this too much, the main message is that Q functions as an expansion parameter, and we have a situation where the classical contributions are small and they balance against the quantum corrections. It's somewhat similar to Banks-Sachs fixed points in QCD with a large NQCD with a large number of flavors near the edge of the conformal window. Now, this has solved the equations in the wormhole region, but not the equations outside the mouths. So in principle, these two mouths they look like particles that have opposite mass, have opposite charge and some mass, so they will attract each other and they will fall into each other. And one way to prevent that is to make them orbit around each other. Of course, you'll say, well, this will emit gravitational radiation and so on, but that, if they are far enough, will be a small effect, and this will give a rather long-lived state, where the lifetime of the state is much longer than the time it takes to go through the wormhole. The time it takes to the wormhole, as measured for the observer that stays outside, is L, this parameter L that we discussed, which is a factor of Q bigger than the size of the mouse. And as seen by the observer traveling through, on the other hand, the proper time for that observer traveling through is just simply RE, so the size of the black hole. So it's much shorter than L. So there is a big difference between the two. Now, we have only argued that these are possible long-lived solutions, and I really don't know of any simple way of producing these configurations if they were not initially present. So that's an issue if you wanted to actually make these things. Now, as we said, the matter that we required is even present in the standard model, but only at very short distances. So you can make in this way, or you could imagine conceivably imagine solutions that are very, very small, so microscopically small. But you could postulate a suitable dark sector that leads to the formation of such wormholes. So for example, you can add a dark Q1 gauge field and add a large number of massless for the fermions that could enhance these effects and lead to the black holes that we discussed. So that's one way to do this. Or more generally, you can have a dark Q1 gauge field plus a conformal field theory, 4D conformal field theory with the U1 symmetry that is such that when you add the magnetic field, it leads to now a 2D conformal field theory with a large number of effective fields. Now, in both cases, we can have large wormholes, but the travel times for the first kind of wormhole is very long if we want the theory to be weakly coupled, so bigger than the size of the universe. So if we just for fun, or science fiction purposes, we wanted to imagine whether we could have a wormhole that can be traversed by a person. So then it should be large enough that we are not killed by the tidal forces. The tidal forces are proportional to the curvature, which is 1 over RE squared times the size of or maybe half the size of the person. And that should be less than the maximal accelerations we can tolerate, which is apparently around 20 g. Of course, this is just some vague numbers. And just putting in these numbers, you get that the size of this wormhole should be bigger than 10,000 kilometers. So it's so of order the size of the Earth. And this is much bigger, of course, than the naive size, which you would have thought that it should be a size bigger than the size of a person. Of course, this is because we are very frail and very sensitive to these accelerations. Now, one way to get a wormhole of this size and with length which is not too long is to consider the Randall-Sundrum 2 model. So this is a model for physics beyond the standard model where you have 5D, have an extra dimension where the extra dimension together with our 4 dimensions form a space which is ADS5, so a space with constant negative curvature. And this extra dimension is infinite in one direction, what's sometimes called the infrared direction, but in the UV direction, it's finite and contains some boundary conditions. And the boundary conditions are such that the graviton is free to vary, or the metric is free to vary. And this leads then to a configuration, this leads to a geometric construction, which is conceptually the same as a theory of 4D gravity plus a 4D CFT coupled to a 4D CFT. So the 4D CFT is somehow given by the ADS5 space, the ADS5 gravity theory. So we can consider this to be a theory which has some extra dark sector, where the dark sector is a conformal field theory. We can also add a bulk U1, 5D U1 gauge field with boundary conditions leading to a 4D U1 gauge field. So we also have the U1 gauge field that we were talking about. And when you put a constant magnetic field for this 4D gauge field, that leads to a constant some magnetic field for the 5D gauge field, and it leads to a flow from ADS5 to ADS3, and that can be interpreted as, again, giving rise to massless 2D modes. And for our purposes, for constructing these wormholes, what we want to do is to maximize the 2D central charge. And this turns out to involve maximizing the radius of the fifth dimension. And so if we wanted to just to wonder whether this is at least compatible with the laws of physics we know, the current limit is for the size of extra dimensions about 50 microns. This comes from the experiments looking at extra dimensions. And taking this value plus the previous minimum value for RE to allow for a person, we get that the smallest value of L that is possible is about 10,000 years. Okay, so 10,000 years is what would take you to go through this wormhole that you could traverse. Now, what is the five-dimensional geometry that you get when you look at this wormhole? So I should mention that the construction of the wormholes is essentially the same as what we discussed before with the massless fermions, the same conceptual steps. The details are different because they involve solving for a 5D geometry, but given ADS-CFT and the facts that we know, the physics of solving Einstein's equations with constant curvature end up being similar to considering conformal field theories, we find that the effective description is very similar to what we discussed before. But nevertheless, it's useful to look at what the final geometry that we get through this method is. The geometry is essentially that it has the topology of, first let's discuss the ADS5 geometry. So we have the Planck brane here denoted in blue, and then we have the extra fifth dimension going down. So far away we have just ordinary ADS5 space, and here the warp factor goes to 0 as you go down. Okay, so this is the infrared region of the ADS space, ADS spacetime. Then the Planck brane has a shape which is the shape of the wormhole, so it goes into the fifth dimension, and it's sort of like a little hole, or really quite literally a wormhole that goes into this fifth dimension. And then we had these magnetic field lines that we were talking about before, and we had these circles that the massless 2D particles were having, and we're moving around. And if we, so in the full geometry, the circles can be filled, are filled through this extra fifth dimension. And the geometry of this space is, so here near the center, is that of ADS3. So this is a portion of ADS3. This is related to the fact that these modes traveling along these field lines are behaving like a 2D CFT whose gravity dual is ADS3. So more precisely, it's ADS3 times S2 with DS2 having a fixed size. So as a fun application, as a fun science fiction application, we can think of this as future ecological galactic travel. So 10,000 light years is roughly the size scales of the galaxy. And as we mentioned, the time felt by the traveler is of order the size, that 10,000 kilometers, and that works out to be a time less than a second, about 0.1 seconds. So that's what it would take the person falling in to travel through the wormhole as seen through her or his own experience. Of course, the person that stays outside would see that you need more than about 10,000 light years to travel through. Of course, the same effect is present in flat space without any wormhole if you travel at very high speeds. So if you just accelerate and travel to speeds close to the speed of light, of course you would age less than someone who would stay outside, who would not travel at these high speeds. Now the ecological part is that no fuel is required to accelerate and decelerate. You just are accelerated by the force of gravity and then again decelerated by the force of gravity. Okay, so that's the fine application. Of course, there are many practical problems. The most important one is that our universe is probably not described by this particular Randall-Sundrum model 2 that we discussed. Even if it was described and you could have this type of configuration, any object falling in is highly boosted. So the boost factor for someone here in the center is about 10 to the 12. And so even the CMB falling from the other side would be enough to kill the traveler. So that's a bit of a problem. And of course, we said that we didn't have any simple mechanism for producing the wormholes in the first place. And also another issue is that the dark sector has to be extremely cool. It has to have a temperature less than the inverse 10 to the 1,000 light years. Otherwise, we'll heat it enough so that we'll form a non-extremal black hole as opposed to these wormholes. So the reheating process and so on has to be such that it does not heat up this dark sector. Now, I mentioned that one of the motivations and one of the reasons to get to these solutions was this relation between black holes and quantum systems. So I briefly in this transparency will discuss this a little bit. So one of the central hypotheses in the study of quantum black holes is that they can be viewed as quantum systems. So if you stay outside the black hole and all its geometry can be replaced by a quantum system with a finite number of qubits or Majorana fermions or a finite number of degrees of freedom, finite entropy. And these connected geometries, such as the Schwarzschild solution or the full Schwarzschild, maximally extended Schwarzschild solution, or these wormholes that we discussed, can be viewed as entangled quantum systems. So quantum systems which are in a particular state where there's entanglement between the two things. Now, these two black holes are somehow near each other. I mean, they're far away, but there is some influence between the two. So there are fields that go from one to the other, these massless fields we discussed. And this leads to, can be interpreted as leading to small interactions between the quantum systems. It's a bit like the van der Waals force that leads to an interaction between the atoms, between two atoms that are at some distance. And then going through the wormhole, so what geometrically corresponds to going through the wormhole is similar to being teleported by this small interaction. So you go into one of these quantum systems, you are completely destroyed and mixed with the quantum system, but these small interactions are kind of teleport you to the other side, and then you are unmixed and reconstructed in the other side. So that's how things are interpreted from the point of view of these quantum systems. And all the information is really, so from this point of view of the right-hand side of this transparency, all the information that is contained in the person who's falling is really transferred via the outside CFT. So it's via the two-dimensional modes that live outside the black hole. So the picture is that you fall into one of them, you are broken into pieces, transferred to, the quantum information is transferred through the outside to the other black hole and then reconstructed. So that's the picture, that's the outside picture, or the picture from this quantum description on the right-hand side. And there is some consistency check of this picture that a little calculation you can do that counts the maximal number of bits that you could transfer by sending signals through the wormhole, and you work it out, and it turns out to be equal to the central charge of the 2D CFT, which is also the amount of qubits that you can send outside through signals outside the wormhole. Okay, and I think understanding the various steps in this relationship is what many of us were doing, and is somehow what led to, we were doing this mainly in simpler models, simpler black hole models, like condensed matter analog of black holes and so on. And then we wondered whether it was possible also to have this type of solutions in 4D. So in conclusions, we discussed some traversable wormholes constructions in 4 dimensions. They require special matter consistent with relativity, but not exotic in the sense that it was inconsistent with relativity and quantum field theory. And this matter is present in the standard model at very short distances, and similar matter can be present in previously considered extensions of the standard model. I don't personally think that those extensions are likely to be realized in nature, especially the Randall-Sundrum 2 model. But the solutions are interesting, mostly for what they teach us about what's compatible with the general principles of relativity. And they also have some interesting interpretation in terms of entangled black holes. Okay, thank you.
Okay, thank you for this very nice presentation. So, questions for Juan? I think there is a comment in the chat by Lisa Randall.
You can ignore that. It was just a comment about the likelihood of any particular model.
And there is also a question by R.D. Verma. Is it possible for the wormhole mouths to move away from each other so that the condition on time travel, on the travel time is eventually violated?
Good. This is a very good question. Yeah. So the formulas that we discussed have a length L, which is independent of the distance, but that was only for distances that are less than the length L. Once the distance d becomes comparable to the length, the equations change slightly, and the length L is always bigger than the distance between the two mouths. You can still solve them. It's very similar to what we discussed, but the equations are such that the travel time is always bigger than the distance between the two black holes. And just to be a little more precise, so in this construction is bigger by a factor of about 2. You could have some alternative constructions that were done in the paper by Grado, well, the paper I quoted in the beginning by Marolf and collaborators. And in that paper, they considered instead of magnetic fields, they consider strings that go between the two black holes. And in that case, the distance is only slightly, the length L or the time through the wormhole is only slightly bigger than the distance d. So that's kind of like the shortest you could make them. And it's still compatible with the principles of relativity. I don't know if this answered your question.
I don't see any reply from Hardy, so I think it's satisfied.
I do have a question. Yeah, well, you mentioned about what happens with one massless fermions. Now, my question is about what happens with many massless fermions, in particular in the limit of infinitely many massless fermions, because if energy would increase, so what happens to the wormhole?
Yes, so in principle, so if you have more massless fermions, the central charge of the 2D theory becomes larger, and the wormhole L, this length of the wormhole becomes shorter. Okay. Yeah, so you could consider formally a very large number of massless fermions. It is unreasonable to consider, even in principle, to consider a number which is such that the 2D central charge is bigger than the extremal entropy of the black hole, which is of order q squared. That wasn't the case for the cases we discussed, but if by taking just arbitrarily a large number of fermions, you would violate that, because that would make the entanglement entropy of the quantum fields through the wormhole bigger than the extremal entropy of the black hole. We think that that should not be possible. But we think that this is not possible based on this type of, within the set of weak gravity conjectures and so on, that when you make the number of fermions too large, the effective cutoff on the field theory drops below the Planck scale, right? And it drops more and more as you put more species of fermions, sort of like the species bound. Yeah, what I discussed before is also the species bound, not to violate ideas about black holes. So that's one bound you have. This bound is not too strong, and you could make relatively short wormholes with using this. However, another issue that you should consider is that when you put a large number of fermions, the effective coupling of the 4D gauge field has a factor of G times NF, so times the number of fermions. And this effect is quite restrictive. So if you want the U1 gauge field to be weakly coupled so that you can trust the discussion, you have to somehow restrict the number of fermions. And you have to restrict it enough that you could not make a humanly traversable wormhole purely adding species of fermions. We tried species of fermions, and we also tried increasing the U1, the number of species of U1s, and we couldn't have a humanly traversable wormhole that well with a traversal time which is less than the age of the universe with those ingredients, only with those ingredients. Now, given, and this kind of led us to this ADS5 discussion or Randall-Sundrum 2 model, because the problem there is that some part of the theory becomes strongly interacting, and well, a strongly interacting theory is what an ADS5 is describing. So that it was natural to try to check whether it is possible with the ADS5.
Okay, thank you.
So we have another question in the chat by Arun. I can read the question. So it's about human traversability. You mentioned that tidal forces can be a problem, but unless the separations are very large, the oppositely charged black holes should also be emitting very large electromagnetic fluxes in their neighborhoods. So is this a problem for human traversability?
Yeah, so the idea is that the separations are very large, right? So we were talking about 10,000 light years. So we don't expect that they would be moving very slowly, and I don't think that's an issue. Notice it's a dark Q1. So even the magnetic field we're talking about is a dark Q1, which is not supposed to interact with our matter.
Okay, thanks. Other questions? Comment?
Hi, I have a question.
Please go ahead.
So do you have any comments about stability of these wormhole solutions in the RS2 scenario? Because, for example, for the black holes, we know that there are some problems with the stability of the black hole since the horizon would extend into the bulk.
Right. Well, so these configurations do not have horizons. So anything that we discuss with horizons will not apply to this configuration. We did not do a stability analysis of these solutions. I expect them to be perturbatively stable. Well, for the previous case of the U1 and so on, we don't see any candidate instability. So all the other, I mean, we took into account the lightest modes, and all other modes have higher masses. So there is no instability, and I expect the same for the RS construction. These are all perturbative instabilities, so sort of tachyons and so on. This configuration will be unstable to the emission of magnetic monopoles. So,
okay.
But that would be a non-perturbative process, and we expect that to be exponentially suppressed if the magnetic monopoles are very heavy. In the Randall-Sundrum 2 discussion, there are no magnetic monopoles, but in just the geometric construction. But because of weak gravity conjectures or whatever, they should be added. But the idea is that they would be added at a sufficiently high scale that it would not matter for what we discussed.
Thank you.
We have another questions from Paolo Pani in the chat. So when spinning, are there ergo regions in the space-time? And if so, they can be perturbatively unstable when spinning due to the absence of horizons, which is called ergo region instability.
Right. Yeah, that's, well, we consider non-spinning black holes. So each black hole is charged but not spinning. I mean, of course, they are rotating around each other, but not with some spin. If you make this black hole spin, this same massless degrees of freedom we were discussing would extract the rotational energy pretty efficiently, and they would cease to spin quickly. So this is just in the first part of the discussion that we discussed magnetic black holes. We should, well, I should have mentioned that if they were initially spinning, they would quickly cease to be spinning. So yeah. So in some sense, these you could say that these massless fields are very efficient in taking the rotational energy out. I could be a little more explicit. This is intimately connected to the processes in our universe that extract energy from rotating black holes. So the Blanford and Senyak discussed this, and one of the approximations they used is the idea that for very dilute plasma, you have this force-free electrodynamics, which is a form of electrodynamics where if you have a tiny electric field, it's quickly screened by the motion of the plasma. And in this version of electrodynamics, this version of electrodynamics is an approximation to general magnetohydrodynamics. And what happens is that a constantly rotating charged black hole and so on, magnetically charged black hole, would just lose energy. So normally you, in ordinary electrodynamics, in order to emit radiation and so on, it needs to be a time-dependent configuration. It should be like a rotating dipole and so on. But if you have just simply a rotating monopole, that can transfer energy to infinity. And it's this effect that, well, it is this effect that, well, takes energy out of supermassive black holes or black holes in general, Blanford and Senyak discussed, that also applies for this for magnetically charged monopoles.
Okay, thank you. Paul is satisfied. So I see there is a raised hand by Shahriar Sikander. Please unmute yourself.
Thank you. It's probably a very naive question, and it's about the the very last part of your talk. I was just trying to understand the channeling of information through the wormhole.
Yes.
Did you really mean classical bits or qubits at the end when you threw them in?
It was difficult for me to hear your question. I think, yeah, let me see if I can.
It was just a point of clarification at the end. Did you mean classical bits are being thrown in the wormhole or qubits?
There could be either classical or qubits. Yeah, let's say qubits.
Okay, and what happens through the wormhole? Is there an actual quantum circuit which acts on these bits, or it's the exact same information that comes out?
When in the geometric description, the fields essentially move freely through the wormhole, experiencing, of course, some redshift factor and so on, but they they come out essentially on the other side, right? That's the geometric description. So there is the fields just move through the wormhole essentially freely, like moving through free space, free fall in space. That's the picture in the right-hand side of this transparency, right? The geometric description. Is that clear?
Yes.
Now, the same picture from the quantum side, where we replace these two mouths of the black hole, but two mouths of the wormhole by two separate quantum systems that are in an entangled state and interacting via the massless fields outside. then what's happening is different. So what's happening in that picture is that the qubits or classical bits go into these quantum systems, and they become very mixed with the quantum systems. There is a lot of scrambling, something called technically scrambling, that each qubit is mixed with all the other qubits that form the system. And then the small interaction that is due to these 2D massless fields, or the fermions that move along the magnetic field lines outside the two mouths, transfer the information to the other system. And then the information is somehow rebuilt on the other side.
Even after the scrambling, you can actually rebuild the entire same information.
Yes, it's important that it has to be scrambled. It's thanks to the scrambling that the small interactions can transfer the information from one side to the other.
I see.
Yes.
Thank you.
Yeah, it's a bit similar to, well, at least let me make first a vague analogy. It's like if you have two coupled harmonic oscillators and you put an oscillation, let's say, in one of them, after a while that oscillation appears in the other system, right? So the first one stops oscillating and then the other one starts oscillating. It's somewhat similar to that, but a little more complicated because you need the scrambling and so on.
Yeah, no, that if scrambling can be explained in the simple harmonic oscillator case, that would be nice.
Yeah, I think that's probably not possible, but it's
so please go ahead. So there is a question from Arti, a follow-up question actually on the distance. So again in the chart, but I can read it. So if the distance is very large, so that the travel through time is continuously modified, do the mouth feel any additional forces due to being connected to the other mouth?
So the idea is that we are moving the two mouths. No, the additional force due to being connected with the other mouth is small. It's a very small binding energy that the system has. So there is a non-trivial binding energy due to the connection, and it goes like Q over L, right? Q was the charge and L was the distance. So that was the energy that we were minimizing over in one of the transparencies. So the actual minimum is that binding energy. It's negative, so it's an energy. The total mass of the system is less than Q. But it's importantly for distances that are small enough, it's independent of the distance, so it doesn't lead to a force. The derivative with respect to the distance is 0. If you make the distance large enough, larger than L, then it does give you another contribution to the force between the two systems. So it does indeed give an additional contribution to the force. It's subleading, I mean, smaller than the force due to ordinary gravity.
Okay, thank you. We have another question about CP. So is CP symmetry relevant to this construction? Actually, so I also have a comment on this. So yeah. For instance, so the theta term can be relevant in the case of a curved space. So do you expect effect in magnetically charged black holes? Some like periphase or something like this?
Well, I mean, when you have a theta, well, I think you're asking if you have this U1 theory and you add the theta term, yeah, then the black hole will also develop an electric charge. I haven't looked at this, but presumably will develop an electric charge, and that will be problematic with this massless fermions. I don't know exactly what happens in that case.
And about CP symmetry, violation of CP symmetry, considering the weak interactions. So do you think it's relevant? I was mentioning the theta term as a possible source.
Yes. I don't know. I have not looked at this, so I expect it not to be too relevant, but I don't really know.
Okay. So a question from Roberto Franceschini. So if this configuration exists, should I imagine that a notion of reciprocity still exists? For instance, can I imagine to traverse the wormhole both in the case I happen to live in the plane and I want to pass by the tube, or vice versa if I happen to live in the tube?
I feel I didn't understand. Could you repeat the question a little more slowly?
Can you read the chat? Maybe it's better if you read the chat.
That's better. Okay, so by living in the plane, I assume it's you live outside the wormhole, and then you can jump in and then go out, right?
I think so.
Now, if you happen to live in the middle of the wormhole, let's say you are living at the very bottom of the wormhole, then it would be very difficult for you to come out, because you have to climb out a very big gravitational potential well. There is a very big redshift factor between the bottom of the wormhole and the exterior. So if you have somehow no kinetic energy, it's difficult to come out. It is possible in principle, but very difficult. Maybe that was the question. I'm not sure whether that was the question.
Let's see if Roberto reacts in the chat. So in the meantime, let's see if there are other questions or comments or curiosities for Juan. No, Roberto is fine with your answer.
Yeah.
I don't see any additional questions. So I think that I can thank you on behalf of the audience for this very interesting seminar. Thanks a lot.
Well, thank you all. Thank you for the questions and best wishes. Yes, thanks for the opportunity to present.